So the next talk in this session is by Ying Zhao, and she will tell us about diagnosing collisions in the interior of a wormhole. Please take it away.
Hello, everyone. Thank you very much for allowing me to present to speak here. And I hope everyone stays well. And this talk will be based on a couple of about diagnosing collisions in the interior of a wormhole. It will be based on a couple of papers we put out recently with Felix Hill and Alex Stryker. So first, I will give some motivations. It's well known that two distant black holes can be connected in the interior through a wormhole. So here's the Penrose diagram. And such an Einstein-Rosen bridge can be interpreted as an entangled state. And this is the famous statement of ER equals EPR. But this also presents a mystery, because two signals sending from two different boundaries can meet in the interior. If Alice and Bob jumps in, they can meet the interior. On the other hand, there are no boundary interactions. So how do they interact? So when they meet, so how do they know what to do? So so this is a mystery. And today I will try to illustrate part of hopefully part of this, try to illustrate this from the point of view of a quantum circuit. So here's the outline of the talk. First, we will very briefly review thermal field double and quantum circuit in the interior of an eternal black hole. And then we started to look at the meeting in the interior of a wormhole, and we will interpret this as an overlap of perturbations in the quantum circuit. The meaning of this hopefully will be clear later. And then we try to be more quantitative, and we look for a boundary quantity that can diagnose the collision. In particular, we will see that a particular 6-point function can diagnose the collision. And then we will study in more details about the overlap in the quantum circuit and compare it with certain properties of the bulk about the post-collision region. At the end, I will point out some unanswered questions. So first, a very brief review of a bulk tensor network and quantum circuit. It was pointed out by various authors that the bulk geometry reflects the minimal quantum circuit preparing the state. I took this picture from this paper of Lenny Susskind because I feel like this is very clear to illustrate the idea. So it's like you imagine if you have thermal field double, you start from some Bell pairs, and these lines represent Bell pairs, and the left panel is a quantum circuit. As lifetime increases, this one gets longer. As right time increases, this leg gets longer. So the meaning of red line is that this is roughly speaking, that we modeled black hole dynamics by a hidden Presco type circuit. What we mean is that at each time step, the qubits are randomly grouped into pairs, and on each pair, a randomly chosen 2-qubit gate was applied. And the key insight is that once you get a quantum circuit like this, you can lay it out horizontally. And then this corresponds to the wormhole geometry. So if we apply unitary time evolution to the circuit, the state gets more complex and the minimal circuit gets longer. The Einstein-Rosen bridge also gets longer. It's a well-known fact that Einstein-Rosen bridge gets longer as time increases. We identify circuit time, dimensionally circuit time with boundary time as d tau is equal to 2 pi over beta dt. I mean, in the rest of the talk, basically when we talk about time, we quite often will set beta equal to 2 pi and just use t. Let's start from the simplest case, thermal field double. We represent thermal field double by S-Bell pairs, and the corresponding wormhole geometry has minimal length. Notice that the lifetime increase this way, right time increase this way. Here we are looking at the time at t equal to 0 slice. Then we time evolve it. When we time evolve it, this picture illustrates the time evolution. Let's say we group them into pairs, and these two orange dots represent a 2-qubit gate acting on this pair, this pair, this pair, this pair. And there is a key properties of these orange gates is that they can be undone from either side. We will call them healthy gates, and the meaning will be clear later. As this gets longer, the Einstein-Rosen bridge also gets longer. One property is that in this case, without any perturbation, then the number of healthy gates per unit time is constant. So the number of healthy gates here and here is constant. let's say if we want to ask about the total number of gates in this region, in this part of circuit, then it's basically the number of gates here times the length of circuit here. Now let's look at perturbed thermal field double. So we correspondingly on the black hole side, we apply unitary operator. We send in some perturbation and at a particular time. And the perturbed thermal field double was represented by epidemic model. Basically, we imagine that there's so first of all, we represent the perturbation by extra qubit. Why? Because the perturbation will increase the black hole thermal entropy. So we represent the increase of this thermal entropy by an extra qubit. And we imagine this one carries some disease. And any qubits that interact directly or indirectly with the perturbation will get perturbed relative to the original circuit. So any qubits that, that have interacted directly or indirectly with this extra guy will get sick. And these red lines, we mean the sick qubits. And these red dots, we mean the sick gates. This is just a toy model. Okay, then coming back to the topic of this talk. What we're really interested in is the quantum circuit with perturbations from both sides. Let's say one from Alice's side, one from Bob's side. And here is one just a simple illustration of a circuit. Let's say something coming in from left time, then there is a quantum perturbation coming in that grows towards the left side. There's a perturbation that comes in from right side, then there's something comes in and that grows to the right side. Our proposal is that, let's say when the time TWR is larger than minus TWL, the two perturbations, notice that the two perturbations do not have overlap in the quantum circuit. Correspondingly, the signal sending to the bulk hit the singularity before they have a chance to meet in the wormhole. The more interesting case is this case, when this time is arranged this way, such that minus TWL is larger than TWR. Then once we draw the quantum circuit, we will see that there will be certain part of quantum circuit where both perturbations appear. The two perturbations have overlap in the quantum circuit. The proposal is that correspondingly the signal will collide in the wormhole. And the larger the overlap is, the stronger the collision is. So once we have a qualitative understanding, let's try to go more quantitative. If we say that the collision in the wormhole interior is due to the perturbation, is due to the overlap of the perturbation, then how do we diagnose this from boundary point of view? The rough idea is that we need some quantity that can quantify the overlap in the quantum circuit. To proceed, let's think this way. Imagine experimentalists Alice and Bob try to build a quantum state in their laboratory. They start some shared EPR pairs. Let's say the dots here represent EPR pairs. And they implement the following circuit. In the left panel, we represent the case where the circuit does not have overlap. Then Alice just, let's imagine Alice has left side, Bob has right side. Then Alice just put in the perturbation, then does her time evolution. And Bob can just put in his perturbation and does his time evolution. But on the other hand, if in the quantum circuit, the two perturbations have overlap, then before inserting the perturbations, both Alice and Bob have to do backward time evolution. Let's say we start from EPR pairs. For Alice, first evolve backward, then towards the left. First evolve backward, then towards the right. And this will make the procedure complex. At the end, there is a time fold in the circuit. As the fold grows, the collision gets stronger. So we see that what we just mean, that overlap in a quantum circuit just means this time fold. In order to diagnose it, what we will do is that we will think of the entire circuit as a single complicated operator preparing the state, and we will quantify the size of this thing. So a very brief review about the size of an operator. Roughly speaking, the size of an operator quantifies how the number of fundamental constitutes this operator is made up of. And it was an idea that's brought up by Feynman many years ago in string theory. And recently, Lenny Susskind, he proposed that the growth of size can represent the increase of momentum when something falls into the horizon. Basically here, we want to further explore this connection and relate to the size of some particular operator to some interior properties. To be specific, we consider operator growth in SYK model. At infinite temperature, the size is just defined as basically this is just the fermion counting. I mean, if you stare at this a little bit, you will see that this gives the average number of fermions made up this operator. And notice that this infinite temperature size doesn't depend on the state. It's just the property of the operator. But once we include the background state, let's say at finite temperature, the size was defined by these people as the infinite temperature size of this operator applying on a thermal background rho to the 1/2. We subtract off the size of thermal background rho to the 1/2, and then we do a proper normalization. If you expand this out, then it's easy to see that the thermal size of single fermion, let's say psi1 of t is a Heisenberg time evolution of a single fermion psi1. The thermal size of this can be related to an out-of-time ordered 4-point function, which grows exponentially until it saturates at scrambling time. One property we will use later is that let's look at the definition of size and the relation to this F4, the 4-point function. This is the size. This is the maximal size. 1 minus the maximal size. So this basically gives you the probability of being sick. This is the size. As the sick, we mean it's affected by this extra qubit. And 1 minus this is the probability of a gate being healthy with one perturbation present. Let's come back to our case. In our case, we want to study the, recall that we have thermal field double, we perturb it from left side, we perturb it from right side at different times. The operator that builds the circuit described above is composed of 2 perturbations. Let's say thermal field double, rho to the 1/2, we perturb it from left side, we perturb it from right side. Then we will take A and B large and positive, basically mean that we do some positive amount of time evolution. And in order to detect the presence of the fold in the circuit, we define size of this operator with 2 perturbations as follows. It's pretty straightforward. You take the infinite temperature size of this operator. You subtract out the infinite temperature size of the operator without the perturbations. Basically, you infinite temperature size of this thing subtract out size of background. Then you do some normalization. And why does this quantity work? Recall that the goal is to detect the time fold. And we see that when there is a no fold, what this gives is the size of this, infinite temperature size of this, subtract out the infinite temperature size of this. When there is a fold, we have infinite temperature size of this guy, subtract out infinite temperature size of this guy. We see that without the fold, the renormalized size does not grow. Just from the pictorial, later we will go into the detailed calculation, but just from pictorial point of view, you see that this does not grow. But in the case when there is a fold, the fold will make a non-trivial contribution to the size, to the difference of these two. And this contribution grows as the fold grows. So our goal is to compute this quantity and try to characterize the existence of this fold and how large this fold is. Just as the size of single perturbation operator is related to an out-of-time ordered 4-point function, the renormalized size of 2 perturbation operator can be written as a 6-point correlation function. And this is just by the definition of a size, and you just can expand out. It's straightforward to check that it actually can be written as a 6-point function, and it has a very simple geometric meaning. Let's say from thermal field double, we send something from TWL from left, from right at TWR. Then we take the correlator at large time AB. That's it. Next goal is that we need to calculate this 6-point function. I mean, our approach, it mostly follows from the calculation in this paper. I mean, they did some calculation by 4-point function. We generalized their method to the calculation of a 6-point function. And here's the contour representation of the 6-point function. I mean, you need 6 contour, and it's that means this quantity is maximally out of time ordered in a certain sense. And we won't go into the details about calculation in this talk. I mean, for more details, you can either look at our paper or look at this original paper on 4-point function. Roughly speaking, we compute the correlator by performing the path integral over time reparameterizations T of U weighted by the Schwarzian action. So this is Schwarzian action. These are the coupling bilocals representing the coupling between the operator pair to the time reparameterization modes. It's the details is in the paper. And here I will only give the result. There are various properties of the result that I hope you can pay attention to. First of all, we take AB large. then the correlator F6 is only a function of TWL plus TWR. This is exactly what we want. What we want is to diagnose if the collision happens or not. And by boosted symmetry, this is only a property of the sum of this time. And after some calculation, here is the integral representation of the correlator with large AB. The detail doesn't really matter, but roughly speaking, if you look at this form, this has a form of a correlator. And this P1 and P2 is, roughly speaking, is the momenta of the bulk quanta created by the perturbation. We can do this integral by saddle point approximation, and this is what we get. We also did a calculation by geodesic approximation in both 2D and 3D. Here's what we get. We see that the saddle point approximation and the geodesic approximation give you exactly the same result if you identify there's a certain parameters. So, I mean, it has a rather simple form, but here I will just focus on some of its properties. Recall that what we're interested in is the size that prepared the circuit. It's 1 minus F6. So here are its properties. First of all, it only grows for negative the sum of this time, TWR plus TWL. It basically stays 0 for positive TWL plus TWR. This is expected as there's a no collision for positive the sum of the time, so it almost stays 0. As we inject the perturbation earlier and the sum of time becomes more negative, the size starts to grow exponentially in this time. This is consistent with the fact that the collision energy, if you compute the collision energy, you will see that it grows exponentially in this time. When the sum of a time here is larger than 2 scrambling time, the size saturates at its maximal value. I think we are more familiar with the saturation at 1 scrambling time in the past. That's because we are considering 4-point function. Here we see the saturation at 2 scrambling time because we are considering a 6-point function. So on the gravity side, a large black hole has formed and the collision happens exponentially close to the singularity. Once we know how to diagnose the happening of a collision, the next question is that can we get more details about the detailed properties about the collision by, say, looking at the more detailed property of the quantum circuit with overlapping perturbation? One quantity here I will pay attention to is that let's focus on overlap region. And we ask the total number of healthy gates in the overlap region. I mean, the total number of this orange gates in this overlap region. They have the property that they can be undone from both sides. What does this mean? It means that they are meaningless for each boundary system alone. They are only meaningful when we have both left side and right side. So we say that these healthy gates are somehow, they have to be in the shared interior. These healthy gates are stored in the post-collision region in the shared interior. When we say that certain gates is stored in certain region, we mean it in the sense of, say, CV duality, complex volume duality, or complex action duality. What we mean is the increase of number of the certain gates correspond to growth of certain region. But here, what we want to do is want to estimate the number of healthy gates here and make a comparison with the collision with the property of the post-collision region. We first try to estimate the number of healthy gates in the overlap region. And in order to do that, we need to study another 6-point function. It basically just take our earlier 6-point function and set A and B equal to 0. We call this F6 prime. First, note that F6 prime depends on both time T1 and T2. And what does this mean? You look at its form. It's 1 minus, again, it's 1 minus some kind of a size over maximal size. So it's if you stare at it more, probably don't have time in this talk, but if you stare at it more, it's a probability of a gate being healthy with 2 perturbations present. Recall that earlier we have 4-point function. That's the probability of a gate being healthy with only 1 perturbation present. So without doing much calculation, if you follow the epidemic model, I mean, epidemic model is say that this perturbation is something that affecting more and more qubits. From epidemic model, the number of the probability of being healthy with 2 perturbations will be the product of a probability of being healthy with each one of them. This is just a qualitative estimation from epidemic model.
You have 5 minutes left. Thank
you. Now we can actually evaluate this 6-point function. F6 prime in Schwarzian with the same method as before. And we indeed see some kind of factorization. It's a product of 4-point functions times a particular something so-called connected 6-point function piece that was first pointed out in this paper. And we see that because this connected piece actually stays of order 1. This orange dots represent connected piece. So it is indeed a product, almost a product of 4-point functions. And here is the form of the result by after a saddle point approximation. And the exact form doesn't really matter, but here I want you to understand its meaning. We say that this F6 prime basically gives you a probability of being healthy, let's say a probability of picking a healthy gate at this time. And if we want to ask the total number, what's the total number of healthy gates in the overlap region, we basically do a time integral from TWL to minus TWL, from TWR to minus TWL of this F6 prime. And I won't write down the detailed answer, but I just want you to pay attention to the fact that it's only a function of delta t. It doesn't care about exactly what is TWR or TWL. It only cares about how large this overlap is. And if you play with this a little bit more, you can basically estimate its time dependence with delta t. You will see that it first grows linear in delta t, then it decreases linear in delta t, then it stays almost 0. We want to compare this quantity with the space-time volume in the post-collision region. So what happens in the post-collision region is that a larger black hole will form. Let's say before the collision, the black hole has a horizon radius RH. After the collision, the horizon it will have horizon radius RH tilde, and RH tilde grows exponentially in the time separation of the collision. The geometry was studied by various people before. And we do the calculation in a BTZ black hole. That's what we get. The space-time volume is a post-collision region. Again, the only thing I want you to pay attention to is that it's a function of delta t. I mean, it's only a function of delta t. It doesn't depend on detail of TWR just by the boost symmetry. Now we want to do a comparison of the total number of healthy gates in the overlap region. It's a function of delta t. And the space-time volume of post-collision region, it's also a function of delta t. We see that both of them has the same behavior, that first linearly growth with the delta t, then linearly decrease with delta t, then basically stays very small. Actually, on top of this linear growth, there is some small exponential corrections. They also match, but it's not clear from these pictures. Here is the time derivative of this. We see that except for the very early time and the near 2 scrambling time of saturation, these two basically have the exact match. So, I mean, this is basically all I have, but at the end, I will point out some unanswered questions. A big unanswered question, as we all know these days, is about singularity. Throughout this work, we assume the existence of a space-time singularity, which can prevent a meeting of signals that are sent in too late. Because that we recall, we said that if when TWL plus TWR is positive, then they don't meet. But this is not true for charged black holes. So how to understand the collision near inner horizon for charged black holes? We have no understanding about that, and our quantity is not sensitive to that. But recently, there is a paper trying to explore that regime. And also about singularity. So this entire picture of a quantum circuit in the interior is only sensitive to a portion of the trajectory of infalling object when it's close to the horizon. And from picture of neutral black holes, one tends to say that at a singularity, the perturbation has smallest size and becomes simple. Why? Just you imagine you send something in at left times 0, and you send something from right times 0, and the two perturbations barely touch each other. And on the bulk side, they meet at a singularity. But again, this picture doesn't work for charged black holes, so we couldn't say anything conclusive. Another thing that how broadly does this meeting occur in general quantum systems? We expect the discussion to hold when the system has a bulk dual, and which is just for the discussion in the talk. But for more general quantum systems, the meaning of meeting is not even clear. But we expect it's some concept that should be as general as a notion of ER equals CPR. The last question is the most concrete one, and it's something that we have been working on for a while, but with very little progress. It's that if we want to use the growth of size to diagnose the interior property, how should we incorporate the microstate information in the definition of a size? Related things are also explored by a recent paper from a group of people at UBC. That's all I have. Thank you.
Thank you very much for a nice talk. We have 4 minutes for a few questions. Mihailo.
Thank you for the great talk. So just to check, am I correct that your actual calculation is in 0 plus 1D on field theory side?
On field theory side, yes, we did a calculation in Schwarzian, but my collaborator knows CFT much better than me, and what he said that he expects that in higher demand, at least in 2D CFT, it will behave similarly.
So my question was basically how difficult would it be to do it on the bulk side to basically imitate the 4-point function calculation of Schenker and Stanford and do the diagonal approximation in gravity?
How difficult it is to calculation in bulk side?
Yeah.
It's not too difficult. It's how to say, it's tedious. You need to keep track of the post-collision region, the change of geometry, but it's doable. Mm-hmm. And we have it. So we did in the bulk side, we did it both in bulk dimension 2 and 3. The calculations in the appendix.
Okay. Thanks. Thank you.
Simon.
Yeah, thanks for the nice talk. So when you're talking about related the 6-point correlator from as kind of way of quantifying this growth of complexity.
Yeah.
I wonder if you could comment on, do you have an interpretation of a 6-point correlator directly as a kind of scattering process or what?
I think this is more or less a scattering process. We send in something from left from right, then we set up scattering process in the interior. And then what we do is that we detect this by looking at the correlators at some large late time. I think your question may be to see that if we can get a scattering amplitude, this kind of thing. And in order to do that, we need to get the collision product out. I mean, we had some attempt in the paper, but I'm not sure if that answers your question. Of course, it's very interesting to study the detailed property of the collision, like the amplitude, but so far.
No, I was just thinking about, I think you more or less answered, but I was specifically thinking, so like you have, if I understand your kinematics, maybe that's what I don't get. So you have, I thought that you had somehow 2 or 4 operators in the past, 2 on each side, and
yeah, yes.
I don't quite see the like what the final what the final state is in this process.
Oh, so this is not a, so what this 6-point function gives us is not an amplitude.
It looks like an amplitude square to me, right? Where you take an amplitude and you multiply it by complex conjugate, so you have you have a product of the in states.
Yeah, yes, you can write as a product of 2 states, but I don't know how to write it as an amplitude. It's what we had in mind is a correlator on a collision background.
Yes.
It would be interesting to write it like in 4-point function, write it as an amplitude. I don't know.
Yeah, for the 4-point function, it was very clear. It was 2 things in the past, 2 things in the future. It was like the kinematics were very, very, very transparent.
Yeah, the kinematics of this should also be clear, but I'm not sure if I can be written as an amplitude. I mean, it would be really nice if one can say extract the collision amplitude of the collision in the interior.
Okay, thanks.
Since there don't seem to be any more questions, and since the time is up anyway, let's thank Ying again.